Right, so lecture 3. In this lecture, we are going to look in depth at a couple of mechanical problems where we first have to identify simple harmonic motion and then answer a couple of questions about it. Right, so for the first problem, let's consider a very classical, very simple horizontal spring mass system in which we've got a spring with spring constant K, and that satisfies Hooke's law, and there's no friction in the system, and the spring is attached on one side to the wall and the other side to the block, and it's pulled a short distance and released. And then now we've got to prove that the mass is undergoing simple harmonic motion. Okay, so this problem I'm going to do in full, showing all the steps and not omitting anything. The idea being that the way that I'll approach it is exactly the same way I'd approach a far more complicated problem that might be at an angle or involve multiple springs or extra masses or whatever. Okay, so I'm going to start with setting up a nice diagram. So let's make a nice sketch. So let's suppose our wall is on the left-hand side. It doesn't really matter. And here is my mass, and it is attached to the wall by a spring, and I want to describe its position, so I'm going to include an axis system, and because in general things are going to be going on in more than one axis, let's put a y as well, because here there are forces in the y direction even though they just cancel. Okay, my mass is m, the spring constant is k, and I'm after the displacement of this function to see how it is moving, so x of t. So we say, now I've introduced things here. Oh, sorry, I missed the y. Good. Now we introduce terms here. K and m are specified in the question. X and y self-explanatory. X of t, what does that represent? So write down what it is. So x of t is the horizontal displacement. From equilibrium position, or I can just say that x equal to 0 is the equilibrium position. Okay, equilibrium position. Right, now let's write down what our forces are. So I've got the spring force acting here towards the left as I've set up the diagram, because if 0 is here, then it is being stretched out. The spring is being stretched out as I drew it. So force is to the left as I set up the diagram. So let's put the leftward force just a little bit above the spring, so it's not right on top of the spring. But we understand, of course, that the force is acting here. What other forces are involved? Well, we've got the weight. And there is a normal force from the surface. You could also have just set up a normal force diagram like you might have used in first year, just a single point with the force in that direction and one up and one down. Okay, or you can include it in the graph like this. Right, so let's see. Yeah, that's the entire diagram. Okay, so this is an excellent way to start with this kind of problem. Okay, so now I want to indicate that I've got simple harmonic motion. So we saw that how I go about this is just applying Newton's second law with the forces. So that just says that the sum of the forces, the net force, is mass times acceleration. And my forces consists of a spring force and a weight and a normal force, and this must be equal to mass times acceleration vector. Now I know that there's only going to be movement in the x direction here, so I can say that this will be the mass times the accelerations component in the x direction times the unit vector in the x direction. Okay, and what are these forces? The spring force is equal to minus k x times unit vector in the I direction. The weight we know, because I chose y to be positive in upward direction. This is minus mg times the unit vector in the y direction. If I chose y downwards to be positive, then this would have been plus mg. And the normal force in this case will just be minus the weight. If it's a setup where the spring is at an angle, then of course the weight and the normal force won't cancel. Okay. Right, so let's substitute. So here I have minus k xi, and these two cancel. So I could have written it here instead. Okay, is equal to m ax I. Okay, and I can rearrange this a little bit. So let's take that. All right, so I can just write. Let's include this step. Minus kx is equal to m, and let's write this as the second derivative of the displacement function, which we know to be the case. And if I rearrange this, bring this term over, and write it on the left-hand side, then I've got second derivative of x dt squared plus, and I'm just going to write it immediately in that form of the simple harmonic motion differential equation. So that's going to be divided by m. So square root of k over m squared x equal to 0. And let's call this differential equation 1. Okay. So this tells me that since 1 is the differential equation for simple harmonic motion, the mass is undergoing simple harmonic motion. Okay, and there is the full complete answer for this kind of problem. Right, so B, find the displacement, velocity and acceleration of the mass as a function of time that results from pulling the mass 10 centimeters and then releasing it. It's given that the mass is 25 kilograms and K is 2,500 newtons per meter. Okay, right, so just for easy reference, let's quickly write down the differential equation again. So the second derivative of x with respect to t plus square root k over m x squared equal to 0. And let's call that, well, this was what we called equation 1 on the previous page. Now we're also given initial conditions. What is the first condition? It's that the mass is pulled 10 centimeters and then released. So we can, let's take t0 to be when we release it. So we're told what x of 0 is. And it's equal to what? 10 centimeters? All right, so now this is going to depend on how you set up your diagram. So how did we set up our diagram? Let's see again. In this diagram, in which direction is pulling? It's towards the right. Do you agree? So in other words, x of 0 would be 10 centimeters. Okay, not minus 10 centimeters. So you're going to have to see that your initial conditions are correct relative to how you set up the diagram. Okay. So this is, in other words, 10 centimeters. So let's just make everything SI, so 0.10 meters. Don't lose your significant figures, right? So 0.10. All right, and what's the other condition then? When it's released, its velocity, in other words, v of 0, is equal to 0 meters per second. Good. Right, now I want the displacement function. Okay, so now I'm going to fall back on the theory from which I know the general solution of this, and that is the general solution of 1 is x of t equal to a cos omega t plus phi. And now we've got to use the initial conditions and the given values to find out what all of these constants are. Now we can already find what omega is. Omega is this term in the differential equation, so I can immediately write on what omega is. That's square root of k over m. So that's square root of 2,500 over 25. So in other words, that is 10. So I can immediately write a cos 10t plus phi. Good. And I've got initial condition in terms of velocity, so let's write down the expression for the velocity as well. So this will be minus 10a sine of 10t plus phi. Good. Okay, so now let's use these initial conditions. First one, x of 0 is equal to what? It's equal to a cos phi. and it should be equal to 0.10. And we'll return to this. Let's call this 2. Now you might intuitively already know that A should be 10 centimeters. If we pull the mass by 10 centimeters and release it and there's no friction, then you might know already that that's going to be 10 centimeters back and forth. Amplitude will be 10 centimeters. But we're going to assume that we don't know that yet. We have a strong suspicion that it is the case, but we're going to work through the mathematics and see if the mathematics suggests it as well. Well, why would we want to do it? It's not going to be a waste of time, even though it might seem obvious. It is a way to check that the mathematics as we set it up is correct. If it turns out to not be the case, then that shows us there's something wrong somewhere. Either we don't understand perfectly what's going on, or the way that we set up the mathematics is wrong. So let's not jump to any conclusions, and let's see if it does work out that A must be 0.10. Now let's use the second condition. So that is the derivative at 0 is equal to minus 10A sine of phi. And that must be 0. Okay, now A is just the amplitude, and so A is definitely non-zero. Otherwise, X is just, well, 0, and so we know already that's not the case because the thing is moving. So this term is non-zero, so I can divide it out. So that means that sine of phi is 0. And what does that mean? What are the values of phi for which that is true? That's just n phi, where n is z. So one of these, okay? And that's clear, of course, why. I mean, if you draw sine, then it's 0 here, and at pi, and at minus pi, and at 2 pi, and so forth. Now we've got to pick which one it is. So if you have a choice, we're going to go through them and try to pick the phi that works, that is the smallest and absolute value. So we're going to start first with 0 and see if that works. If that doesn't work, then we'll try pi, or we could try minus pi, although these two will be equivalent. Okay, so let's start with the smallest one. So let's try phi equal to 0, and in the other equation that we have, and let's see what that gives us. So then that would mean, what is cos of 0? That would be A cos 0, which is equal to just 1, so A equal to 0.10. And that is good, that is right. Remember what I said in the previous lecture. When we set up the equation for the simple harmonic motion in this form, we will always be able to write it in a way such that A and omega is positive, always, just as long as phi is chosen correctly. So we're picking the smallest phi for which the other initial conditions, or other initial condition in this case, is satisfied, and such that this standard that we impose on ourselves is satisfied. That is, that A and omega is positive. Again, as I said, it is not the mathematical imperative. It just makes it easier to read the equation and interpret it. So we'll always do that, make A and omega positive. Okay, and phi equal to 0 makes A positive. If, for example, phi would have suggested, if, for example, the first phi we tested suggested A is equal to minus 0.10, then we would have tried the next phi instead. Okay, so remember that, but we'll probably see that in the next question as well. Okay, good. So I have A. So that means, do I have everything? I've got omega, I've got phi, I've got A now, 0.1. Perfect. So everything works out the way we thought it would. So x of t is therefore 0.10 cos of 10t plus phi, and the velocity function is therefore equal to minus 10a, so in other words minus 1.0, so I have to write a little bit smaller, 10t. Oh, what is that? Sorry, no, that's wrong. No phi, we know phi is 0, minus 10t, and we know that the acceleration is then, if I differentiate that again, I get minus 10, so minus 10 cosine 10t. Okay, and there we have it. Okay, so for exercise 4, we've got the vertical arrangement. which is otherwise very similar to the exercise 3, just the mass. With the it's given it's 1.5 kilograms, we're given the spring constant, we're told that it satisfies Hooke's law, and we're additionally told it's 25 centimeters long when it's unstretched, uncompressed. And we've got to find by how much it is stretched at equilibrium. Okay, that will be easy, and then prove that it satisfies simple, or that it undergoes simple harmonic motion when disturbed, and then also find the frequency of that motion. Good. Okay, so we start by making a nice diagram. That's always where we start. So let's say that is my ceiling, and I've got my spring hanging down, and I've got my mass, and it's mass M, and its spring constant K, and I'm going to be interested in how this thing moves about. So I'm going to introduce an axis system. Then let's make downward positive. You could make upward positive, but I think I think it just makes it a little bit easier, some of the steps, if you choose downwards to be positive. Right, so let's call that y of t. Okay, right, and so we want to, okay, so it's clear that y of t represents the vertical displacement, and I want this to be vertical displacement from equilibrium. So to indicate that, we're going to say that 0 is the equilibrium position. All right, so if it is at 0, then it just stands still and remains there, which means it is necessarily already a little bit stretched at 0. So the amount by which it is stretched at 0 will equate to an upward spring force that cancels out the weight of the object. Now, speaking of which, we've got the upward spring force and the weight downwards. Good. Now this amount by which it is already stretched at equilibrium, let's call that d. So stretched length at, well, you could say equilibrium or at y equal to 0. So y equal to 0 is clear enough. So there, for example, would then be the unstretched length, and that would be at minus d, right? Because remember, downwards is positive. Good. Okay. Now for A, we have to find out what d is. And that is very simple. Of course, that is just at y equal to 0. Yeah, so we have to find out what d is, right? So how much is it stretched if the block is at 0? Good. Okay, so that is just where the force, the spring force and the weight cancel. Now at 0, what is the force? It is minus k. How much is the spring stretched at 0? It is stretched by d. It's minus kd in the negative y direction, or it's kd in the negative y direction, plus, now it's plus mg unit vector in the y direction, not minus mg like in the previous case, because now downward is positive. Good, 0. All right, so in other words, kd is equal to mg. So what is it that we're after? D is equal to mg over k. And notice we keep the symbols right until the end if possible. Now when I can finally calculate it, we put in the units. So the mass is 1.5 kilograms. Let's take that as 9.8 meter per second squared, and k is 150 newtons per meter. Good. Okay, and that's easy. That we don't have to actually calculate with the calculator. 1.5 over 150 is just 1 over 100. So 9.8 over 100 is 0.098. So 0.098 meters. Good, that is the answer. So 9.8 centimeters. All right, I just asked for by how much it is stretched. Okay, so I can leave it at that. They didn't ask how many centimeters or anything like that. Good. Now, let's move on to B. B asks us to prove that if it is disturbed, like here, if it's pulled down a little bit or pushed upwards, whatever, then the resulting motion is simple harmonic. Okay, so we saw how that works. We use Newton's second law. And we say that, which is that the sum of the forces, so the net force is the mass times the acceleration, but everything here is occurring in the y direction. So that will just be a subscript y and unit vector j. Good. And so what are the forces? There are two. The force plus the weight equal to m-a-y-j. And the force is going to be minus k. Okay, now here you've got to be careful. What is for a y value? So let's say for this y value here, when the block is here, what is the upward force? It's going to be minus because it's in the upward direction. If y is positive, or if y is greater than minus d, actually. But what is the actual force upwards? It is going to be this multiplied by how much it is stretched. And by how much is it stretched at this point? It is not y, it is y plus d. It's this distance, and this distance is y plus d. From here to here is y, and from there to there is d. So y plus d. Okay. And the way that is easy, that's still mgj equal to, and let's keep it like this, mayj. Good. All right, so everything in the y direction. So let's simplify. Minus ky minus kd plus mg equal to may. Good. But look here, kd, mg. These two are the same, so they cancel, so this falls away. So all that I'm left with is minus ky equal to ma. All right, now let's write this in a better form, or more familiar form. And now it's the same as the previous problem. Let me just rearrange it and get second derivative of y with respect to t is plus square root k over m squared y is equal to 0. And let's call this 1. So 1 is the differential equation for simple harmonic motion. Again, you can leave it at that way, or if you want to be more complete. So the motion is simple harmonic, or simple harmonic motion. Good. All right. And now don't forget that we were asked another question. We were asked, what is the frequency of the motion? Well, we know that this in here is in our definition of simple harmonic motion, that inside is omega, which is the angular frequency. And I know that, okay, so let's write it like this. So omega, let's see, we know that the period is equal to 2 pi over omega. So the frequency, I just write it this way because I remembered period first. That's easier for me to quickly figure out. So the frequency is 1 over this, so omega over 2 pi, and omega for us is the square root of km, so it is 1 over 2 pi times the square root of k over m. So in other words, that is square root of k over m, and that I can calculate. 1 over 2 pi times square root of, okay, what do we have here? Okay, it still works out easily. So 150 Newton per meter over 1.5 kilograms, so that works out to 100. So it is, this works 100, so square root of that is 10. So it's 10 over 2 pi, so that is 5 over pi. And let's see, what does that work out as? I'm not going to leave it like that because these look like measured values, so I'm going to give my answer to the correct number of significant figures, which in this case will be 2. So 5 divided by pi, so 1.6 hertz, 1.6 oscillations per second. Okay. Right, so now for exercise C, we want to know what is the maximum distance between the mass and the ceiling. And we're given some initial conditions. Initially, the block is just at its equilibrium position, and then it is shoved or pushed downwards to give it an initial downward velocity of 2 meters per second. Good. All right, so what is it that we want? If I want to know what this maximum distance is, I want to know what y is, so then I can get its maximum value. I know y is going to be that form a cos omega t plus phi. So I just want its amplitude. It's the a value in the expression for y, for simple harmonic motion. Good. So I want to solve for y. I've got a differential equation for it. I've got two initial conditions, so I should be set. So, all right. So let's start by writing down this simple harmonic motion differential equation again, just for easy reference. So, because we're on a new page, squared k over m squared y equal to 0. Good. We called this 1, and we're given the initial conditions that y of 0 is 0. It's at its equilibrium point when it's given its initial velocity, and that initial velocity is, okay, now plus or minus, that's going to depend on how you set it up. We chose downward to be positive, so it's going to be plus, positive 2.0 meters per second. Good. All right, now I want to solve for y. So let's start by writing down what the general solution of 1 is. That is y equal to a cos omega t plus phi, where omega is square root of k over m, which in the previous question we already, or in part B, we already saw was 10. So it is a cos 10t plus phi, and the velocity y dot is therefore minus 10a sine 10t. Well, this actually kind of looks very familiar. We had the same function in exercise 3, but okay, no matter. Right. Now let's start. Let's start by substituting the initial conditions and see if we can find for a and for phi. Okay, so y of 0 is what? It is a cos phi. A cos phi, and this must be equal to 0. And a is non-zero because otherwise y is just a flat line, and I know that there is motion of some sort. So a is non-zero, so I can divide it out. So I get that cosine of phi is equal to 0. And where is cosine function 0? It is at pi over 2 and all multiples of pi. So that's a general solution of this. Good. All right. So multiple possibilities. We're going to pick the one closest to 0, which solves the initial conditions and makes a positive. All right. And second condition, let's put, shall we put it up above? Let's put it on the side. So y prime of 0 is equal to minus 10a sine of phi, and this must be equal to 2.0. Good. Right, is that all correct? Yes, that's correct. All right, so now what do we do? We've got possibilities for phi, and we've got this expression, and if I substitute any phi value in here, I can solve for a. All right, now let's see. Let's start with pi over 2. So let's try, or let's do it here. Let's try phi equal to pi over 2. What happens then? Then we get minus 10a, and sine of, what is sine of pi over 2? It is 1, right? Sine at 90 degrees is 1. So that tells us that a is equal to minus 1 over 5, which I don't want. It's not mathematically wrong, but we want our amplitude to be, we want our a term to be a positive value. That is the convention that we use. Okay, so let's try the next phi value. What is the next one that we'll choose? 3 pi over 2? No, we'll try to pick the smallest one. So pi over 2 doesn't work, so let's pick the next one, which is just as small. So let's try phi equal to minus pi over 2. And when we do, we get minus 10a. And what is sine of minus pi over 2? It is minus 1. And this must be 2.0. So a is equal to 1 over 5. Good. So this is the one that we are going to use. Good. All right. So we have for a and we have for phi. So thus, y of t is therefore 1 over 5 cosine of 10t plus phi over phi is so minus pi over 2. Good, so I've just solved for y. All right, but that's a bit more than I wanted to do. I'm more interested in the amplitude. So what is the amplitude? So perhaps I shouldn't write it like this. So what is 1 over 5? That is 0.20. Yes, we have two significant figures. So cosine 10t minus pi over 2. Good, all right. Okay, so that tells me that the amplitude is, so that's the amplitude of y of t is 20 centimeters. Good, now, where's the graph? What is the maximum distance then? The maximum distance will be when y of t is the y value of the block is at the furthest down. And what is that? That is 20 centimeters below the 0 value. Okay, so what is the distance from the ceiling then? So when y is 20 centimeters, then the distance from the equilibrium point to where the block is 20 centimeters. And the distance from the equilibrium point to where the spring is unstretched is a further, what we calculated, 9.8 centimeters. And the distance from there to the ceiling is that given 25 centimeters. So thus, maximum distance from the ceiling is going to be 20 centimeters plus 9.8 centimeters plus 25 centimeters. Good. And what is that equal to? So that's 20 and 25, that's 45 plus 9.8. So 45 plus 9.8 is therefore 54.8 centimeters, but we can only answer to two significant figures, so approximately 55 centimeters. Okay, so for exercise D, you again do C. This one I'm going to leave for homework, but I will similarly upload the solution just like with other problems that we did. So go and see if you can solve it yourself. So the big thing that's different there is the initial conditions. So now the initial conditions are instead y0 equal to 0.050 meters, the way that I set up the diagram with downwards as positive, and the same initial condition for the velocity, 2.0 meters per second. All right, so go and see if you can solve for y and figure out the maximum distance using these initial conditions instead and see where it goes. We have to make a plan to get, because it won't work out exactly the same way. You're going to have to approach it a little bit differently at a certain point. Okay, all right, but please go and try it yourself first before you look up the solution. Okay, now for the final problem, we have to prove that a simple hanging pendulum will perform simple harmonic motion when deflected by a small angle. Okay, so now this is a problem we'll have to approach with a little bit more finesse and see how we can derive the differential equation for simple harmonic motion for it. Okay, so now we're going to work in 3 dimensions here, and we'll see why in a minute. So let's make a nice diagram and include everything. So let's say the XY plane is like the paper itself, and Z comes out of the page. And Let's try to indicate it like this. Good. And let's suppose that the pendulum is swinging in the page like this, and it is fixed here. So it's got this cord or this string, which we're going to assume has negligible mass. Otherwise, you have to be able to work out center of mass, and it gets more complicated. All right, so what else we want to know? All right, so the pendulum is swinging in the XY plane, and let's say this angle that the pendulum makes with the negative y-axis is theta of t. And how it swings like this. And what are the forces involved? So I'm going to have tension in the string. And I'm going to have a downward force, gravitational force on the pendulum, which we will be able to split up into the tangential component, which we'll just call Ft, and a radial component, which should cancel with the tension, Fr. Okay, and let's suppose the string length is L. Good. Now we introduced a bunch of terms here, so let's name them, make it clear what everything is. So theta t is now the angular displacement in xy plane relative to the negative x-axis, negative y-axis, All right, so that's pretty clear. And let's say the string length is L, and we assume that it has negligible mass, and pendulum mass is m. Okay, so that's everything. Okay, so now we can start. All right, now what we're going to use here is also Newton's second law, but just in a different form. We're going to use Newton's second law for a rotating system of particles. Which states what? It states that the net torque of the particles is equal to the time rate of change of the angular momentum. All right, so this is how you can derive this form of Newton's second law as well. Good. Okay, so let's see what are these terms. If I've got something rotating about some point, and here's the actual thing that's rotating, if the radius vector from origin to this point is r, and there is some net force on it, then the torque is this radius or this connecting vector's cross product with the actual force. So this is torque. Okay, and what other term do we need to know what it is? It is simply the angular momentum. And okay, that's also easy. So if it's relative to some point. So if I've got my object and this connecting vector to the origin is r, and it's moving with some velocity v, then the angular momentum is the mass times this r cross product v. Good. In our case, this thing will just be the pendulum ball or whatever it is. So you can go and look up torque and angular momentum in your physics textbooks. Okay, but I provide the form here. So we need to know how to calculate cross products to do this problem. Okay, now let's start. I want to start with the net torque. So let's see what that is. The net torque is vector R connecting the origin with the pendulum, cross product with the net force on it. Good. Okay. And what is that equal to? So that is the net force on the pendulum is just the sum of this tension in the rope on it and the gravitational force. So it is R cross product T plus R cross product FG. But look, what is the radius or this connecting vector, this R vector? It is the vector going from there to the pendulum. And in which direction is the tension? It's in the same, it's parallel to it. So this term falls away. Okay, so what are we left with? We're left with vector R cross product with f of g. Okay, and what is that equal to? Okay. Well, f of g can also be split up into two components, right? It can be split into this ft component and tangential component and this radial component. The cross product relative to this radial component will likewise to t be 0. So what we're left with is only this tangential component having any bearing on this calculation. So now we have to figure out what that is. So if I've got a vector going from there to there, and I take its cross product with a vector going from there to there, what is its magnitude? All right, so remember now how that works from first year for cross product. It's going to be let's see, it's going to be the length of the one. Well, let's write it on. Let's do it on a separate piece of paper. Good. So for this calculation, I've got my origin. I've got my pendulum. So there is R and its length is L. And there's the tangential force F of t. So what is the cross product of these two? So what is R cross product F of t? So now you have to remember the right-hand rule. So if you have a vector like this, cross product with a vector like that, okay, so then now you have to use that right-hand rule thing. So this is going to be, let's see, it's going to be into the page. All right, now into the page for us is, in other words, into the page for us is in the negative z direction. Remember, z is coming out of the page. So for us, this cross product is in the negative z direction, and we use k for that unit vector. So this is going to be minus. And you remember, if you take a cross b, then it's going to be ab sine of the angle between them. And what is the angle between these two? Always 90 degrees. All right, so this is just going to be minus the length of the two. So it's minus L. It's the length of R. Ft we can still calculate. Minus. Okay, so the minus is there because it is in a negative z direction. Good. And this we can simplify a little bit, because what is Ft? Normal, remember your geometry from high school. If this angle is theta, then so is this angle. This will also be theta. So I can say this is minus L Ft, minus L Fg sine of theta. And it's unit vector. Okay, good. All right, so we just have to be careful here how we're using the cross products, not to get the directions mixed up. Good, okay. Now, all right, now let's go to L. So the angular momentum is therefore going to be the mass times R cross product V, and or also R cross product the momentum vector. Okay, so let's see what this is. All right, so what is V in this case? All right, so now we have to, let's get another piece of paper. Right, okay, so this one. Okay, so here I've got my pendulum, the origin and the R vector, connecting it like this, and it's moving out like this, the theta of t. So at any point, the velocity is tangent to this circle in which it is moving. Let's, for purposes of figuring out what the sign should be, let's suppose that it is moving upwards. Okay, if it's moving upwards, then there is the velocity vector. But how are you going to calculate that? Well, v is, what's the magnitude of this velocity? Is just going to be equal to the length of the distance to the origin, which is L, times the time rate of change of the angle. Now you might wonder why this is the case, and this is one of the big reasons why we use radians for angles. If something is moving around a circle, and let's suppose that the angle that it's making, let's say it's moving counterclockwise, and the angle is given by theta of t. Okay, this is a bit small, by theta of t, and let's suppose that this distance it's gone around for any t value is given by s of t, and let's say the radius is L, then the radius of the circle multiplied by the angle gives you the arc length of this corresponding sector. Specifically, if your angle is in radians, not 4 degrees, for radians, which is a nice property which radians has, which is why radians is far more natural way to designate angles than degrees. So if I differentiate on both sides, what do I get? You get L theta dot, and what is the time rate of change of this S function? It is just going to be how fast v, it's going to be how fast it is moving around. So v of t, how fast it is moving around the circle. Good. So that's where this comes from. So the magnitude of the velocity vector is going to be L theta dot. Okay. All right, so now let's collect ourselves. What do we want to calculate? All right, so we know what R magnitude is and we know what V's magnitude is. Good. We just have to figure out in which direction that this cross product is. All right, now for the same purpose, as before, just now, let's stick with this orientation that is moving upwards, and then let's see what this other sign should work out. What is cross product between R and V in this case? So R and V in that direction. What's the cross product? What is R cross product V? Which direction is it? All right, so right hand rule again. So now it will be out of the page. So for us, out of the page is in the positive Z direction. So this is mass times, this will just be L, so L times the magnitude of this thing, which is L theta dot, as we just convinced ourselves, and it is in the positive Z direction. So K, unit vector K in the Z direction. Good. All right, so in other words, ml squared theta dot in the Z direction. All right, but we're after the time derivative of this. So d dt of the angular momentum is therefore, those are just constants, the mass and the length of the string doesn't change. So it is just ml squared theta double dot k. All right, now Newton's second law in torque angular momentum form thus states, thus that this is equal to that. So ml squared theta dot double dot, let's call it d theta squared dt squared, is equal to minus L Fg is just mg times sine of theta. Good, these two are equal. So let's rearrange this. So if we rearrange this, we get d theta squared dt squared plus, right now these terms cancel out. If I divide by ml squared and bring that term over, m's cancel, l's cancel, so g over l, yeah, plus g over l sine theta equal to 0. Right, there we go. Okay, and does this look like simple harmonic motion? Well, not quite, but this is another nice thing about radians. But sine of theta, and this is, let's look at its Maclaurin-Taylor expansion, if you can go and work that out, minus, it'll work out like this, 5 over 5, whatever, and then extra terms. Sine of theta is approximately equal to theta if theta is very small, or small enough. Which boils down to the case that if theta is in radians, then the slope, the derivative of sine at the origin is 1. So the line tangent to the sine graph at the origin is the line y equal to x, if we're working with x and y, which is the reason why sine of theta, geometrically, is the reason why we can see that sine of theta is approximately equal to theta at the origin. But it's only if theta is in radians. So thus, for small angles, these sorry, now I just noticed d squared theta dt squared. Why is it, what's it doing there? It shouldn't be there. Okay, d theta squared plus g over l theta is equal to 0. So this is simple harmonic motion. Good, all right, so a lot of things going on here, and it amounts to knowing how torque and angular momentum is defined, and then you just have to be careful in figuring out in which directions these cross products are. And then everything works out very nicely, and there's a nice illustration also of why working with radians is a good idea. It's a far more natural way to define an angle. That's not to say that if you didn't pick angles to be in radians, then you wouldn't have been able to show this. No, you still would have been able. Even if you made theta degrees, you would still have been able to show that for small angles it is simple harmonic. It would just have been far more difficult. It would have been more tricky. I mean, you wouldn't have had nice results like the velocity being equal to L's theta dot. I mean, that part would have changed definitely if you worked in degrees, and then this part as well. But in the end, it should still work out to this. Okay, and that's it for the second lecture on simple harmonic motion.